Now, modeling with a composite function is something that we kind of do in physics a lot. So, for example, number 5, we're given the volume of a, well, let's read it right from the textbook before we jump in there, okay? So, let's take a look at what the textbook is telling us, and then I'll explain how we use composite functions. Can you guys see that okay? Let me turn off the lights. Now that doesn't help, does it? Well, let's just read it. It says, in a medical procedure known as angioplasties, doctors insert a catheter into a heart vein through a large peripheral vein and inflate a small spherical balloon on the tip of the catheter. Suppose the balloon is inflated at a constant rate of 44 cubic millimeters per second. Find the volume in t seconds, and then when the volume is v, what is the radius? Write an equation that gives the radius as a function of time. What is the radius after 5 seconds? So this seems important, right? So if you're a cardiologist or a heart surgeon, you don't want to overinflate the balloon because it'll pop the vein. And it probably has some sort of pump, and it probably does actually pump at 44 cubic millimeters per second. So you want to get this right, okay? And so what we want to do, and this is why you use the math in the real world, the first thing that we want to do is it says after t seconds the volume will be 44t, okay? After t seconds the volume will be 44t. How do we know that? Well, we got to solve it. So the first thing we do is we start with the volume of a sphere, which is the formula 4/3 pi r cubed. That's the volume, little v. And so what I want to do is if I'm going to write a composite function, I want to make one a function of the other. So because it's talking about the volume, and our final question was write an equation that gives radius as a function of time. So let's solve this for radius. All right, so I'm going to solve this for the radius and see what we get. So I'm just going to move stuff over to the other side. So I'm basically going to divide this by 4/3 times pi. Whatever I do on one side, I got 4/3 pi. Now remember that when I divide by a fraction, I multiply by the reciprocal. So I really should get 3v over 4 pi. I don't know why that is zooming so weird today. Okay, there it is. Can you see that? And now if I want to get r by itself, I take the cube root of both sides and I get r is the cube root of 3v over 4 pi. All right. Now here's the thing. After the rate in which this thing inflates is 44 cubic millimeters. So the rate that it inflates at is 44 cubic millimeters. Per second. And so I could, that's a volume, cubic millimeters is a volume. I have a volume of 44 times t, where t represents the number of seconds. So if I were to make a composite function of these, I could say the cube root of 3 times my v, which is going to be 44 T all over 4 pi. Do you guys see what I did there? And then lastly, what they wanted, or not lastly, but another thing they wanted us to know was what happens when T equals 5. After 5 seconds, what will the volume of this thing be? Well, we could find the volume of this by saying 44 times T equals 5, right? And so the volume is, what's 44 times 5? Is that 220? Somebody do that on their calculator real quick. Forty times 5 is 200, and then 4 times 5 is 20. It's 220, right? So this is 220. Another way we could write cubic millimeters is to do it like this. But you know what? I was looking, and I said, this looks a little messy. Could I clean that up a little bit? Can I simplify some things in there? Yes, Mr. Adams. Could I do this? Because 44 divided by 4 is the same as the cube root of 3 times 11, because this is 11, and then this is 1. So I could say 3 times 11 is 33t all over pi. Could I clean that up a little bit? Would that be the same? Okay. And so let's just see. So my total, just to verify, if I were to plug in 33 times 5 divided by pi and take the cube root of that, what would my radius at that particular point in time be? Well, it'd be 3.74 millimeters cubed. So my question to you is, and the composite function portion of this is just plugging this equation into this equation. But what are we really, if I was a biomedical engineer, what am I trying to do? What is my goal? See, this is a balloon that's going to go into somebody's vein. And your veins are not very big, but this is a big vein. And it has a diameter, or the sphere. You want the sphere to blow up the basically you want to see how big the radius is. So if I were to take a vein and I were to draw it out, I would assume that I would be curious about the radius of this particular vein, right? Because I don't want to blow up the vein. So I want to put air into this balloon in such a way that I could control the radius, because what it does is, normally what happens is, what this is used for is, if there's plaque around the vein, what it does is it restricts blood flow. And so they put the balloon in there, and what the balloon does is, as the balloon expands, it opens the vein back up. Now it'll have a bigger, because the plaque is built up on the vein, but you want this hole to be a certain size so the blood can flow through it. So as a biomedical engineer, what I want to do is I want to leave this vein a certain size so the blood can flow through it. But I can't get into somebody's vein and measure how wide it is. I can't even look at it. I'm going to take a catheter and insert it into somebody's vein, so I have to have a way to determine how big the balloon is. And the only way I could do that is, well, to figure out how long it takes to blow the balloon up to a certain size. And so I could work backwards. Now that I have this equation that makes the radius a function of time, as long as my pump's working properly, I can calculate how many seconds I need to pump that air through. And if I pump the air through to the balloon for a certain amount of time, the balloon will get just the right size. I can open up the vein and the person can live a little longer. Does that make sense? Good. Any questions?